All right, let's draw some examples of molecules that don't follow the octet rule. So it gives us a couple things to think about here, like determining the number of valence electrons available in the molecule. That's always something that you can do if you're ever in doubt, kind of like that carbon monoxide example, where you think you're drawing the dots and it just doesn't seem to work out right. Try that. Add up the total amount of valence electrons available and distribute them so that everybody gets an octet that wants an octet, knowing that there are some cases where we can have more or less, which is kind of what they tell me in step 2. Distribute the electrons so atoms that normally satisfy the octet rule do. Extra electrons can go to atoms that can take an extended octet. Those that can take an extended octet must have d orbitals. So we're talking atoms in the 3rd period or beyond, or the 3rd energy level. All right. It also says to beware that some atoms can form stable compounds with less than an octet. For example, beryllium. Beryllium only has 2 valence electrons. We usually draw them 180 degrees apart to show that these electron groups would be negative and they'd repel. You got 2 chlorine, throw them on there. The negative electrons repel, they're 180 degrees. I draw the dots on chlorine like I normally would, 7 valence electrons, organized as a single and 3 pairs. You can connect the dots, you can circle the dots or whatever to show that you've got 2 bonding pairs of electrons on beryllium. And I know he has less than an octet, but that's okay. What else are you supposed to do? He doesn't have any more electrons available, and it's not an ion. This is stable as is. Don't overthink it. Same thing with that phosphorus pentachloride. Phosphorus has 5 valence electrons, and I normally draw 5 valence electrons as a pair and 3 singles. Often, phosphorus just wants to make 3 bonds. In this case, he's going to make 5. We're just going to bond all 5 valence electrons. So let's throw on 5 chlorine. 1, 2, 3, 4, 5, 6, 7 valence electrons on each chlorine. You kind of rig the single dots so that they line up. Cool. Chlorine number 3. And then the last 2 chlorines, we're just going to split the pair on top. 1 single, 3 pairs. Connect the dots. And there's the last chlorine. Phosphorus can take an extended octet. He's in the 3rd period, which means there would be available d orbitals. So it's okay that phosphorus has an extended octet. But now nitrogen could not do an extended octet. They're in the same group and their electron structures would look very similar, but nitrogen doesn't have the d orbitals available. So yeah, these would be super simple. Don't overthink them. Let's look at a couple other good ones. Chlorine Trifluoride. Weird. We don't have any of that. Doesn't mean it doesn't exist. If I don't have 1 chlorine, I usually put that guy in the middle. But then here's where you run into some roadblocks and you're like, what? How are you supposed to put 3 fluorine around a chlorine? Normally, I do something like that for, whoa, that's a weird looking dot. There. Normally I would draw 7 valence electrons, and I have no clue where I'm supposed to put 3 fluorine. Doesn't that look weird? So here's a good case where the localized electron model fails. If I'm really just going to try to draw this thing by lining up dots, I'm not going to get the correct structure. In true covalent bonding, we share all the available valence electrons. So let's abandon the localized electron model. Sad face. It fails. Into the toilet you go. Instead, we're going to go to our second option. Let's look at valence electrons. In this structure, chlorine carries 7 valence electrons, and so do the fluorines. They each have 7 valence. There are 3 of them. So if I add this up, I have a total of 28 valence electrons to play with. And somehow I need to organize those 28 electrons so that all atoms get a full octet. So you just try something. Try something that seems reasonable. I don't know. Let's put the chlorine in the middle because there's only 1. And then let's just chuck the 3 fluorine on the outside. I don't know. It looks kind of cute. I really like symmetry, and it's all evenly distributed. Fluorine must have an octet, no exceptions. He's only in the 2nd energy level. He can't take more than an octet, and he definitely won't take less. Right now, each dash represents 2 electrons shared in a single bond. So let's give him 8. 2, 4, 6, 8. So let's go around and fill up these fluorines. He's got to have an octet. All right, let's take inventory. Let's see what we got. We have used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used 24 electrons. We cannot add any more electrons to the fluorine. They're done. They're full. So where are you going to put the extra electrons? We still got 4 electrons that we have to use. We have to put them somewhere. Well, if you ever have extra valence electrons and the center atom is in the 3rd energy level or beyond, he's got d orbitals. Just throw them anywhere you want. In the Lewis structure, put them on the center atom. And again, I mean, if they're going to give you a structure that's going to work out, that central atom is probably in the 3rd energy level or beyond. So you just dump the extra valence electrons on the central atom. In reality, they're going to go in d orbitals. Now I do a little inventory. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, boom, 28. We use 28 electrons. Chlorine has an extended octet. He's got 2, 4, 6, 8, 10. Those dashes represent 2 electrons. That's okay. Chlorine has d orbitals. Oh, okay, that's not miserable, right? And I always think to start by trying the localized electron model. I think to start with my dot structure being all prim and proper. But if I get stuck, I abandon LEM pretty quick. And then this is what I do next. Count up the valence electrons you have available. Distribute them in a way that seems logical. You know, the fluorine has to have an octet. And if you have any extra electrons, they'll always go on the central atom. And often that central atom can have d orbitals. So check out this next one. Iodine, 2 chlorine. Ooh, a -1 charge. This sounds awesome. Iodine Dichloride. There's a lot of stuff going on here. First, I'm going to put the iodine in the middle, right? But I'm going to end up with a situation kind of like the first structure. Iodine has 7 valence electrons, so you'd assume that you'd only make 1 bond, which often is the case. So how am I supposed to put 2 chlorine on there? Well, the LEM's not going to work. We're going to have to abandon the localized electron model. And instead, let's just start drawing something. Let's count up the valence electrons available and just start drawing something. So iodine. Iodine has 7 valence electrons. Chlorine each have 7 valence electrons times 2, which would give me a total of 21 valence electrons. But now I have to take the charge into consideration as well. Oh, yeah, because I mean, this is awkward to have an odd number of electrons. Electrons usually like to be paired if the structure is stable, right? Oh, yeah, that's why there's a -1 charge. So you get to add 1 electron from the -1 charge. So we're really going to look for 22 valence electrons. I need to give all atoms an octet that want an octet, and I get to use 22 electrons. So I don't know, just start drawing something. I'm probably going to put the iodine in the center, and let's just link up the chlorines. Everybody needs at least an octet here, because we're not dealing with like little atoms that can maybe take a deficient octet. So let's just go around and see what we get. Each of the chlorine are going to need 6 more, and the iodine's going to need 2 more, 2, 4, 6, 8. Okay, so let's count them. 2, 4, 6, 8, 10, 12, 14, 16, 18. Ooh, I only used 20 electrons. Now, technically, in this case, chlorine and iodine have d orbitals available. They're in the 3rd energy level or beyond. So in that case, if you have to decide where to dump the extra electrons, it always goes on the central atom. They always go on the central atom. And I mean, if it is a legitimate structure, that central atom is in the 3rd energy level or beyond. So you can put them wherever you want. I don't know, maybe I'll kind of like make 2 pairs on the top. Give myself a little more room. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. And since this is an ion, we should put it in brackets with the charge on the outside. That iodine in the center is carrying 2, 4, 6, 8, 10 electrons, an extended octet, which is okay. He's got d orbitals available. And rather than putting them like on the outside chlorine and then trying to decide which chlorine should get the extra pair, it's always most stable to put the extra electrons on the central atom. Nice. That's not so bad. You just kind of have to think of these logically. This last, well, the one below it, this I3 minus 1. Check this out quick. It's kind of interesting because realistically, it's going to be real similar, right? And it's 3 halogens with a -1 charge. So I'm not going to necessarily draw it, but I will mention this. You could draw structures, legitimate structures, that might have like double bonds or triple bonds or whatever. The most stable is always single bonds if possible. So for example, you could do this. If I had like 3 iodines, it's real similar. It's going to be 22 electrons. You could go like iodine, iodine, iodine. And then you could go around and add all the extra dots and give them an octet. And you could say, okay, I got 2, 4, 6, 8. 2, 4, 6. This guy needs 8. And then this guy needs at least 6 more. And so now you could count them up and say 2, 4, 6, 8, 10, 12, 14, 16, 18. I got 18 total. And yeah, iodine can take an extended octet. So I'll just chuck the extra electrons on that central iodine. And then there you go, -1. This is legit. If you drew this Lewis structure, it's not wrong. And again, you could draw this for that iodine chlorine ion as well. Both of them are going to follow the exact same rules. They're just 3 halogens. Those are totally fine Lewis structures. Now, the most stable, my first choice is to go single bonds. But the second one that maybe had a double in there, that's not wrong. It's most likely not the real structure, though. Check this xenon tetrafluoride. This is a fun one. Xenon? What are we doing drawing a Lewis structure with xenon? It's a noble gas, right? It is. Well, little noble gases like helium and neon, they really don't have any interest in bonding. They're very stable. They're nice small atoms with lots of attractive forces between the nucleus and the electrons. But as you get down the group like xenon and even krypton, the atoms are a little larger, which means there's a little less attraction between the nucleus and the electrons, which makes them a little bit more vulnerable to bonding. So again, don't overthink it. If you get something like this on the AP test, and they say, hey, draw an acceptable Lewis structure, don't say, oh, this must be a trick. There's no structures available because xenon is a noble gas. No, they're not going to trick you. This is a legitimate molecule. Although, I don't know where to start. Xenon probably goes in the center, but if I try to follow LEM, the localized electron model, xenon would have like 8 dots, and I don't know where you put the 4 fluorine, right? So let's just start drawing something. Let's count the valence electrons and at least work on trial and error. Okay, so xenon will bring 8 valence electrons to the party. Fluorine brings 7 valence electrons. There are 4 of them. Times 4. Awesome. So we just add them up. Let's see how many valence electrons we have available. 28 from the fluorine. Ooh, this is going to be fun. 36 electrons available. Valence electrons that we can play with. So we just got to kind of do a little trial and error. Try to use 36 electrons. Fluorine must have an octet. Xenon is well beyond the 3rd energy level with d orbitals available. So we can get a little more creative with the xenon. So let's see. I don't know. My first thought is just to put those fluorine around the outside, huh? Fluorine. Fluorine's got to have an octet. 2 electrons in the single bond. So let's go around and give each fluorine 3 pairs. So they have a total of 8. Fluorine, no exceptions. He must have 8 valence electrons. I like drawing these Lewis structures. I think it's like a fun game. Let's see if we can figure it out. Okay, let's see what we got. What's the damage? 2, 4, 6, 8. 8 times 4. Right now we only used 32 electrons. So the extras just go on xenon. Xenon can take extra electrons. He can take an extended because he's got d orbitals available. You can really, on paper, put them wherever you want. Just tuck them in there. It looks kind of goofy. But it's right. I promise it's right. Xenon is carrying an extended octet, and he can. I used the correct amount of electrons. I got 36. The fluorines have an octet, and the xenon is extended. Totally fine. Now again, this is the most likely structure, and coming up very soon in your near future, we'll be able to determine like what's the best structure, the most stable structure, where more than one might exist. You could go a little wacko and try throwing like double bonds and triple bonds in here, and you could get an acceptable structure. For example, what if you were just feeling a little nutsy and you did this? No, this would be somebody that's like completely whacked. Whoa, this is crazy. I'm going to go triple bond, I'm going to go a double bond, and then I'll go a single bond and I don't know, another single bond. Weird, that is just nuts. Fluorine needs an octet, so we'll go around and give him an octet wherever possible. Okay, so he's gonna need 2, 4, 6, 8, 2, 4, 6, 8, and then 2, 4, 6, 8. Now this is kind of wild, and this would definitely not end up being the most stable structure. So I'm going to caution you, don't do this on the AP test. But there's always some kid that draws something wacko like this and says, isn't this acceptable? Okay, well, yeah, they're not going to mark it wrong, but it's not going to be the most likely structure, which is something that we can determine in one of the next videos. So why draw something if it's going to turn out to not really be the most likely structure? Let's count the electrons we used. 2, 4, 6, 8, 2, 4, 6, 8. Hey, we have 32. So the extra 4 just get plunked on the center xenon because he can take an extended octet. Now, we really loaded up this xenon, didn't we? What's he got? 2, 4, 6, 8, 10, 12, 14, 16. Holy buckets, we gave him like 18 electrons. That might be a little unreasonable. However, this is technically not wrong on paper. On paper, a Lewis structure needs to follow like 2 rules. You got to use the correct amount of electrons, which we did, and you have to distribute those electrons correctly. Fluorine needs an octet. He has an octet. Xenon can take an extended because he has d orbitals, which that's where we threw the extra electrons. So both of these would be acceptable Lewis structures on paper. However, we'll soon find that the second one is not likely. It's not the most stable idea, and in fact, it really doesn't exist. So it's kind of the same thing with like these halogen examples. I mean, this is your first thought. This is really the most stable structure. This is the true structure. And it's the same for this iodine one. In real life, it exists as 2 single bonds. But if all they ask you for is a Lewis structure, this is acceptable. And in the next videos, we'll learn how to determine which is the most stable, and maybe like why isn't this the most stable. And now you probably have guesses, like that xenon looks like it's kind of overloaded. So this would be okay. I wouldn't like freak out if somebody drew this on the AP test, but this is better. So don't try to get too nutsy. And really, I mean, if you're trying something that's outside of the box, single bonds are usually your best bet. Don't make it hard on yourself. Just go single bonds and see if you can make it work.